We're back with now the problem of disjoint set union, and today's problem is a divisibility tree. And if you know what a divisibility tree is like, a divisibility tree is a tree which is divisible by the edges of the tree, and the edges of the tree are divisible by 2. Then we are going to remove those components. So what you can see is your task is to remove the minimum number of edges that form the given tree such that the tree converts into a disjoint union tree, so that the nodes of the connected components are left is divisible by 2. So if you see, we will be given n equals to 10 is the total number of edges, and then the edges are given in the form of sets. So I have already told you in the form of sets, like last problem we have discussed about disjoint sets, is like we will take these edges in the form of sets, and then we have to reframe this in the form of a tree. So edges 1 is present over here, and 6. So 1 is connected to 6, 1 is connected to 3, and 1 is connected to 2. That's why they are in the form of coordinates 2, 1, 3, 1, and 6, 1. Similarly, for 2, what we can see is we have 5, 2, and we have 7, 2. So you can see we have from 2, we have 7 and 5, the origins. If you check the other numbers, 3, we have 3 and 1. We have 4 and 3. So from 3 only 4 is there. Let's check from 6. From 6 we have 8 and 6. We have 6 and 1. So you can see from 6 we have 8. From 8 what we have 9 and 8, 10 and 8. So 9 and 8 and 10 and 8 both are there from like this particular tree. Now we have to remove those edges which nodes are even. So the nodes which are even are 1 and 3 and 1 and 6. So after removing 1 and 3 and 1 and 6, we'll get the output as 2. Okay, so yeah, so let's start with this problem statement. And if you are not understanding the problem, there are more examples of edges. Like this is example 1, there is another example 2. So if you just read it, you will get to know what it is going on. Okay, I'm just going to keep it short because this is not a very difficult problem. So what we are going to do is we are going to use a DFS traversal, and there is a minimum edge remove function. So in the DFS traversal, what we are going to do is we are going to take a private int DFS method, which methods will have parameters as list, integer, and this is an adjacent list, int node, int parent, int answer. Okay, so next we are going to keep a counter, say int count equals to 1, and we are going to create a loop. So the loop is used to iterate over the adjacent nodes of the current node. So it to adjacent node of the current node. In this, if the adjacent, now we get, if suppose we get an adjacent node which is not present, then we have to avoid backtracking and we have to continue DFS on the adjacent node. So what we are going to do, we are going to check. So if I not equals to parent, then int c node counter equals to DFS, which is the recursively we are calling this particular function. So we will be passing the values adjacent, I, node, and answer. Okay, adjacent node, I, and answer. Now you will be wondering from where is this answer coming. This answer is present in the main method, which is the int minimum edge. So from there we are getting the answer. Now answer is also there in the parameter of this particular function, so we can get the answer from here as well. We will actually get the answer from here. Okay, so we have done recursively calling this function for counting. Now we are going to have another if condition, if c node modulus 2, because we have to check the even number of nodes. So modulus 2 equals to 0, then what we are going to do is we are going to give answer of 0 plus. So this is nothing but basically checking the total number of count. Okay, so this is the if condition is done. Then we will go the else part. Else we have to count plus plus, which is our regular count. After that the else is closed, the if else is closed, the main if is closed, the for loop is also closed. So here we can write return count. Okay, now let's go with our main function, which is the minimum edge remove function. So in the minimum edge remove function, there are edges and n as parameter. So what we are going to do next is we are going to just create an adjacency list. So list of type integer, and the adjacency graph is being created equals to with the size n plus 1. So new list n plus 1. Once we have created the adjacency, now we have to initialize each node. So for initializing a node of the adjacent list, int I equals to 0, less than equals to n plus plus. So for initializing adjacent of I equals to new array list, we have initialized. Now after initializing, we have to, so I will write it over here, initializing the list, populating the list with given edges. So how we are going to populate? So for int edge is the edge present in the 2D matrix edges, adjacent of edge dot edge of 0, adjacent of edge of 0 dot add edge of 1, like this. Similarly, I'm going to take this, I'm going to paste this, put it as 0 and 1. Once this is done, what we're going to do is we are going to take the answer array. So int answer equals to new int 1. So why I'm doing this? Initializing, and we are basically initializing an array to store the answer, or the ini and array to store the answer. And what is the answer? Basically, number of edges to be removed. Okay, so once the edges are removed, we are going to perform a DFS traversal. Okay, so for performing a DFS traversal, we will call the DFS function, we will pass the adjacent list, the starting value, -1, and answer. So why we are doing this? We are basically performing DFS node assuming 1 based indexing. So assuming 1 based indexing for DFS search. Now return answer of 0. So let's go compile this. Line 83, list integer. So what I have done is a list of integer type equals to new array list to do this. So we have successfully completed today's problem statement again on disjoint set, and I hope you like the explanation. See you tomorrow in our next video.